All right, welcome everyone to another exciting edition of the Makercast. Whether you are a seasoned builder, a tech tinkerer, or just here for some creative inspiration, we are thrilled to have you with us today. We've got a fantastic lineup of projects and a little something special at the end. So grab your favorite tool, get comfortable, and let's dive into the world of making. So first up will be Jonathan. I'm the host. I will go last, I think. So we start with John. So maybe you introduce yourself and then you show us your project.
Great. Thanks for passing the buck, Moritz. I'm Jonathan Oxer. I'm from Melbourne, Australia. Are we just going to do an introduction or should I show projects as well? What do you think?
Well, I think most of the people know you, but
okay.
You can do a quick introduction, I guess.
Okay. So I have a YouTube channel called Superhouse. My interest largely started out in home automation and went in different directions from there. For the last couple of years, what I've been doing is a bit of contract engineering, helping clients take ideas for new products through to production. So I've been doing product design and small-scale assembly. I've really been focused on the pain point between making a couple of prototypes on a bench and going through to manufacturing. There is that very painful area right in the middle where you might want to make, say, 100 or 200 of a device because you need to do field testing, you need to do design validation, all of those sorts of things. And that's the valley of despair, where it's too much for you to build by hand, but it's not really enough to scale up to mass production. And that's really the area that I've been focusing on. All right, so who's next?
I can go next.
Hello,
hello. I'm Christian. I'm originally a physicist. I work as a software engineer in industrial automation. And in my spare time, I mostly do software stuff as well. But I also like bringing my software creations back into the real world using digital fabrication machines, like 3D printers and laser cutters and CNC mills. I also help run the Fab Lab. That's where I have all these machines. Yeah, that's what I do.
And then last but not least, Kevin.
Hi, everyone. So I'm Kevin McAlee. I make robots and I make videos about how to build robots, how to code, how to use Raspberry Pis and things like that on YouTube. And then I write them up for my website, kevsrobots.com. So I've been doing this about 3 years, I think, now online. But yeah, loving making stuff.
So I'm Moritz, also known as Envy, but also VMO, because that's my company name. I am actually a software developer in my full-time job, but also like to tinker a lot and do some electronics projects. Just what I think is fun to do at that time. I got a lot of projects actually that I'm working on. So if there's a new opportunity for a new project, I will probably start it and then leave the rest rotting away or something when I get back to them. So yeah, that's about me. So I think, Jonathan, you can go first with your project and please show us what you did.
Sure. Thanks, Moritz. So as a result of some of the projects that I've been working on over the last few years, I've had a lot of need for testing. And if you've done electronics manufacturing, you would be very familiar with test jigs like this sort of thing. It's a device where you take the device under test, the PCB that you want to test, put it into a jig, and then pull down a lever. It pushes down some test contacts onto the device, and then you can load firmware, run tests, do all of those sorts of things. And over the years, I've designed many of these sorts of devices. I have, in fact, I have a whole plastic tub here full of random test jigs. And so many of them use the classic lever sort of mechanism that pushes down on the top of it. And I've done boards where I've designed tester circuit boards with test pins, and they give red and green pass fail sort of things, little laser cut assemblies. So there are many different jigs that I've put together over time. And the part of the problem is that a lot of it is reinventing the wheel, because when you start making a test jig for a new project, there are a whole lot of things that you have to do that are common to many of the projects. You need some kind of system that is going to be executing the test. So you need a software environment for that and a machine to run it on. You need a mechanical chassis that allows you to make all of the electrical connections. There is I/O that you might need. You might need to drive digital pins. You might need to read digital pins, and also analog input and output. You need power supplies to power the device under test. And I got really sick of redoing all of this work. So what I ended up doing was beginning a project, which went through a few name changes. At the moment, it's called Testomatic, and it is basically a system that I've been using for a little while now in its first version, and it is just going into its second version. And this is a picture of the Testomatic V1.0. The idea is that there is a chassis which is common to all of the different things that you might want to test, different types of circuit board. And there is a Raspberry Pi in it, a touch screen on the front to control it with. There's a label, oh, sorry, not a label printer, it's a receipt printer, like one of the thermal printers you find at the checkout in a shop. There's a barcode scanner. You can see here that there is a camera pointing down. In this particular case, there is a board sitting there which is about to have its firmware flashed onto it. You can see there is a programmer plugged into it through a cable and a header. This is not actually how the system was intended to be used. The test chassis is over here on the left, and there's a big hole in the top. And the reason for that is that there are different modules that can drop into it. And this is an example of a module from the version 1 Testomatic, which is the one I was just showing you. It has a PCB in the bottom, which is the test pin carrier board, and it has all of the little spring-loaded test pins and a laser cut outline so that you can take the PCB you want to test, drop it in, it will be located within these guides, and then make electrical connection with these test pins. And you can see that there are IDC connectors along here. And with my first version, what I had was IDC cables that would run down into the chassis and allow you to interchange these modules. So my goal was to make a chassis that was as universal as possible and to allow me to swap out modules to be able to test different devices. Because typically when you build a test jig in this sort of style, it will be built for one target, and that's the only thing it can ever be used for. So the investment in building the test system is replicated over and over again for every jig. And I wanted something where the smallest possible amount of investment is required for each additional type of board that you want to test. Because in my situation, I'm not just testing one type of board. I'm not in a real mass production situation where I need to test 10,000 of one thing. I have many clients and many different types of boards to test. So I might be testing one board in the morning, and then in the afternoon I need to test something else, and then the next day it's something else. I want to be able to swap out a module and then be ready to test a new board. And that really is where all of this was born. And the general process, so I'll show you the version 2 in just a moment, which is where I'm up to at the moment. But I'll show you the general process here with this photo. The idea is that the device under test is connected to the tester, either by sitting it down on the pogo pins or by plugging in with a flying cable like it's shown in this example. The type of board is selected through the touch screen. At the moment, there is some Python running on the Raspberry Pi which manages the actual execution, like uploading firmware to the target, etc. And the user interface it's kind of embarrassing to admit, but it works well, is Node-RED Dashboard v2. So this is a full screen web browser running Node-RED Dashboard. And that then can connect to MQTT, and it can interoperate with run the Python scripts, pass parameters to them, etc., to execute the tests. So the process is you plug in the board, select what type of board it is, which will be pre-selected if you're doing the same thing over and over again. Zap the barcode with the barcode scanner, which loads that into the test, and then it loads the firmware, does everything that it needs to do, and prints out a receipt on the receipt printer. And that receipt has a couple of bits of information on it. So just as an example, here is, oh, I'll move that out of the way. That's Testomatic V2. You'll see that in a second. So it'll print out test report, what type of board it was, who did the test, what firmware was loaded, and it'll also give you some manual checks to perform, because there are some checks that you need to do that can't be tested automatically. It might be things like, have you performed a factory reset, which needs to be done manually, or have you included a connector in the bag? There might be a loose connector that has to go in with the device. So there is a list of manual checks that the operator can perform, and they can tick them off on that piece of paper. Piece of paper goes in the bag with the device that goes to the customer. And it also records the information locally. So just backing up a fraction. So this is if anybody's interested, this is the GitHub repo. I'm not sure if I can drop this in the chat or something, but maybe we can put this in. And so this basically summarizes the 4 goals of the project: minimizing reinvention, providing enough I/O to make the majority of tests easy. Now, this is a fairly critical thing. What we need to be able to do is read and write analog inputs and digital inputs to the device. But often when you're testing a circuit board, there will be some strange requirement, something that you haven't thought of before, or something that's not particularly common. Now, because I happen to do a lot of automotive related contracting work and robotics work, I do a lot of work with CAN bus. So it's quite common for me to need to communicate with a device under test over CAN bus, and therefore I need CAN bus functionality within the tester. But for most boards, you don't need that. Or maybe you need RS485, or who knows what it might be. Maybe you need a device that does wavelength testing for LEDs to make sure that the LEDs on your device are working properly. There are many, many options. So the way I've designed this is I've provided enough digital and analog I/O to handle the classic Pareto principle, cover the 80% of common cases. And then I've got SPI, I2C, and multiple USB ports to allow you to extend it to add whatever you want. So if you want a CAN bus interface, you can add it to your test module. So also allowing the chassis to be reused, and also integration with external test management and logging. My friend Mitch has been working for the last few months on an accompanying software platform that works with this. And what it does is provide a centralized portal that accumulates the data coming from the tester. So if you have multiple testers, you can be collecting data from each of the testers that then stores it centrally with all of the results of the tests and all of the records of everything that's been done. So later you can look back in time, look up a specific serial number, for example, and see the history of that device, when it was assembled, the test results, and everything else. And what we're working on at the moment is exposing that to our customers so that if they want to look up the history of a device, they can log into the portal and they can see their own devices and obviously nobody else's. So this is version 1, which has been used for a couple of thousand boards now at this point. And this is version 2, which is the version that I've got sitting on the bench right now. This is done with a laser cut chassis This is a side view, and the close side has been removed so you can see into it. You can see the test module up here, and in fact I'll grab that. So this is an example of a test module. What I did was switch to a card edge connector. This was at the suggestion of someone on one of my live streams. One of the viewers came up with the great idea of, instead of using the IDC connectors, why not use a card edge connector? And that way the module can simply slide into place and engage and have all of the connections it needs through the card edge connector. And this is a self-contained test breakout that goes into the chassis, provides all of the electrical connections. It also has an I2C EEPROM on it and indicators for the power rails, so that what the goal with this is to be able to drop a new test module into the chassis, have the chassis identify it, and it knows what type of board you're about to test. So it automatically configures its tests, and you don't need to select what type of board it is. You just drop this in and it says, oh, I know what that is. I'm going to load these tests. And if you want to change to something else, you just unplug it, slide a new module in, and you're good to go for the next tests. So the overall chassis, if we look at it from this point of view, so it's a bit of a mess at the moment. I need to improve cable management, but it's at the point of being functional at least. So there's a touch screen on the front. This is a bigger touch screen than on my first version. It's I think 1024 by 600 resolution. There's a Raspberry Pi down in the bottom. There's a ribbon cable that goes through to the Testomatic PCB that you can see in here, mounted vertically. And this provides a whole lot of functionality that I'll show you in just a moment. Power comes in the back. I'm a total addict to XT60 connectors. I use them all over the place. So my lab power supplies can plug into XT60. Power comes in, and then there are multiple power supplies in here which are all current sensed and controlled for connection to the device under test. So there's a question there, what is the overall size of device under test PCBs that is supported? That's a great question. So one thing that I've been considering is testing panels as well, because I do, with smaller PCBs, I typically assemble them as panels, and they can be 200 by 200 millimeters, you know, that sort of size. Now, this particular chassis is designed to be at least big enough to test boards this size. So what you can see here, for example, is quite a large, like you can see, that's a big PCB. This is a very large PCB. A lot of panels would be smaller than this. And it can be extended trivially in terms of length. It could also be made a little bit wider as well, if that was useful. So if I bring this back over here, also part of the design includes a deck. You can see that this is all open at the moment. I can access all of the wires in here, but there are slots in the side because normally there is a piece of acrylic as a deck blocking this off, covering the internals. But I've got it out at the moment because I've been pulling things in and out and working on the tester. So I just wanted easy access. But normally this is all enclosed, so it's quite protected. And the test module just drops in the top and then slides forward to engage with the edge connector like that. And there are mechanical stops here to support it all. If you wanted to test a larger PCB, it would be trivial to make it deeper. In fact, you wouldn't even need to change the chassis. The module itself could just protrude out the back a little bit, and that really wouldn't matter. And of course, you can do shorter ones. And as part of this, what I'm working on is a reference design for a tester PCB with the edge connector, the power indicators, the EEPROM, and everything else. So that what you can do is use that as a starting point for designing your own test pin breakout board. So about, Geordie asked about 20 by 15 centimeters. Yeah, give or take, something like that. I think this board is 183 millimeters. So it's in that sort of ballpark. And you could fit a slightly bigger board in here if you wanted to. But also adjusting this design is quite easy. I made the design fairly parametric. This was all designed in Fusion 360, and there are variables for pretty much all of the dimensions. So if you wanted to make it a bit wider, you could. If you wanted to make it longer, you could. That's all quite easy to change. What else? Oh, yes. So if I slide this module out, actually, no, what I'll do first is I'll show you a little bit more about what the PCB in there is actually doing. Bolly asked, how much time did it take you to develop this version? Well, it's been done over the space of a couple of months, and that is with the help of people in my live streams. I do a live stream every Sunday morning, and this has been a regular topic. So I've had many, many suggestions and a lot of input from people to help me do this. So this is the PCB that is mounted vertically, and it has separate power supplies for the Pi and for the device under test. So there are status LEDs for main power in plus 5 volt and 3.3 volt rails for the Pi, and then main power in 5 volt and 3.3 passed through to the device under test. Those are all switchable through these relays, and there are INA 260 current sensors, so that you have independent power control to the device under test, and you can monitor the current, so you can detect shorts on the device. You can see if its power consumption is within spec, etc. There's a USB hub, which is passed up through to the test board. So there are 4 channels, 4 USB channels going up to the test board, plus ADCs, DAC, SPI, I2C, etc. And that's just a kind of overall view of how it all fits together. An example of the test pin carrier PCB, and a list of the various features. So as I was mentioning before, one of the issues is that there are many times that you would come up with a specific test that you want to execute that isn't just a simple GPIO or analog or digital connection. Now, I'll just take a slight detour. So Nick asked the question, why did you select Perspex over, say, 3D printed assembly for your prototypes? Partly for speed. I do a lot of 3D printing as well, and that I've used 3D printed components in some of my testers. But what I found is that for laser cutting, I have access to a laser cutter physically here on site, and it means that I can iterate incredibly quickly. So building a structure like this, to build this entire thing, if I laid a sheet of acrylic down on the laser cutter and pressed go, there's probably 10 minutes of cutting, and I'd have all of the parts to assemble this entire chassis. And trying to reproduce something like that using 3D printing, you're talking about days and days of printing. So it means that I can very quickly make changes. Oh, Geordie said I don't see a constant current. Beg your pardon?
It looks a lot cooler, I think.
It does. It actually makes it very hard to show on camera, though, because it's transparent. It's like, yeah. So Geordie said, I don't see a constant current source in the design. Am I right? Sometimes you want to measure with constant current instead of constant voltage. Yes, exactly. There are many avenues for improvement on this design. And so this is where this comes in, this whole expansion issue. Things like programmable power supplies. Now, there are certain products that I work on. There is one of my clients is a company that makes water cannons, and I design all of the control systems for them that move the water cannon, and so it's all CAN bus controlled, and we control solenoids for water flow, start and stop pumps, and all of that sort of thing. And I need to be able to test motor drivers. They are reasonably high power motor drivers, which means that I need some kind of an external dummy load to exercise the motor driver and put it under stress so I can see if it's working properly. And it's that sort of thing that once I started, my initial approach was to think, what are all of the things you might possibly want to test, and then allow for that in the chassis. And I very quickly realized that's not practical. The better approach is to cover the basic functionality within the chassis and then use modules or other external devices for the more specialized purposes. So for example, I have a programmable dummy load sitting just here to my left, which can be controlled over Ethernet. And what I can do is hook that in with a connector into the back of the test module. So on the test module itself, you can put connectors to external devices like external programmable power supplies, signal generators, dummy loads, all of those sorts of things. And then the test chassis can control those. So the test chassis doesn't have to incorporate every single piece of functionality. It can act as the, what's the term? The conductor, and manage the different things that you want to incorporate into your test process. You don't have to build it all yourself. So that's the general approach that I've been taking. And there are certain things that are very commonly required, like you might want to have a USB to serial connection to your device under test, so that in the case of, say, an ESP32 that may not have built-in USB, such as one of the old style ESP32D or E series, you want to be able to flash that. You also need to be able to put it into bootloader mode by pulling GPIO 0 low and hitting reset, that sort of thing. So what I have done is started designing little modules that can be simply plonked onto the test module to do specific functionality. And if I come over to the microscope, just as an example, this is it's upside down. This is a little test module, a serial module with a CP2102N on it, and it's just got pin headers. So the idea is that you could design this into your test module and use one of the 4 available USB channels, because there's a hub built into the test PCB. And then you've got serial coming out the end with control of GPIO 0 and reset. So it means that it's very simple to design the test breakout. So my whole goal here is to make it, I want to do the 80% of the common work and have it there ready to go, so that all you need to worry about is the 20% of the specific work that is required for whatever your project is. So your device under test is going to have certain requirements. Those specific things are the things you should have to think about, not the basics of, I need to build a chassis and how am I going to run a power supply? How am I going to manage measuring current to the device? How am I going to isolate that so that it doesn't short circuit my tester? And all of those common things. Yeah, you can see the 4-port USB hub on there. So that is a very brief summary of Testomatic and where it currently is.
Well, thanks for that. I also have one question for you. So since I'm the software developer guy, I'm curious how the Python code and such works. So how do you actually load a test program onto the device, and how does it, like, how does that kind of stuff work?
Yeah, sure. I have I'm just thinking about whether I should pull it up now. What I have at the moment is a test runner program. It's actually called just testrunner.py, which is written in Python, and it accepts a couple of arguments. One of the arguments is the SKU of the particular device that you want to test, and another one is the serial number. Basically, those are the things you pass to it. You say, I want to test device type rack32, and the serial number is 1234. What it then does is have a number of directories. There is a targets directory. Within that directories for each of the SKUs, and they include a configuration file that's loaded by the Python, which gives it paths to various things, such as what scripts to execute to upload firmware, what script to execute to run certain tests. And that gives you the flexibility of writing whatever tests you want within your own little standalone environment, and the test runner just calls out to it. And it takes the output from that and stores that with a timestamp against the test results for that test execution. That's an area that could do with a bit more cleaning up, but it's functional. It's not necessarily neat. I took a fair bit of inspiration for it from the way Debian packages work. For those of you who don't know, when you install software onto a Debian system, there is a standardized format for the way the software is packaged, and it includes a number of hooks for different scripts. And it gives the software maintainer the ability to define things like, what script do I need to run before installing the software? What script do I need to run after installing the software? What configuration file do I want to put into place? And by creating a template for how all of that happens, it means that you can go in and fill in the blanks and just ignore the parts that you don't need.
That sounds quite elaborate. So
yes,
great work.
It's one of those projects where you sit down and think, oh yeah, I'm just going to make a test system. And then 2 years later, you are far, far down the rabbit hole and realizing that building testers is orders of magnitude more complicated than you ever thought it was.
Yeah, I also thought about creating a test jig for my product that I sell, but it's just so low quantity that it's quicker done by hand, I guess, for now. So yeah, but I do like your project and will probably build one myself in the future, I guess. So
yeah, great.
Well, do you know if anyone
help you do it?
Do you know if anyone else who's using this already, or are you just publishing it for anyone who wants?
No one else is using it yet, but on my live stream, there have been a couple of viewers who have said that because all of this version 2 has only really been taking shape. This physical version that you see here has only existed for about 2 weeks. So this is the new chassis, the new test module format. There are a couple of people in the live stream who say that their companies are considering using these for their in-house testing. So I think there will be a few people using it quite quickly.
Okay, nice.
So Christian, you are next with your project. Thanks, John, for showing us your Testomatic. And yeah, the stage is yours.
Okay. I first have a quick update about something I've shown on the Makercast before. And somehow my hotkeys aren't working anymore. On a previous Makercast, I was talking about these Pew Pew game consoles by Deshipu and how I was trying to get the games running on them, running on the Playdate. And at that time, I only had a quick prototype, but now I have something that runs, and I can quickly show you that. So this is now a Python code running on the Playdate, showing me the Pew Pew menu, and I can select the game here and run it. And so on. I'm not only this yet, but the basic functionality is there. I still want to polish it to make it attractive and easy to use for other people, maybe even to program their own games on it, even though it's not quite as convenient as on a real POP device. But yeah, at the moment I only have the basic functionality. You can also already download that if you want. In the video description, there's a link to my Mastodon, and if you scroll down a couple posts there, you can find a link to the release on GitHub.
But, Christian, what is that display technology?
That is a sharp memory display. You can buy these from Adafruit. It's an LCD, and it's not backlit. It's black and white, 400 by 240 pixels. It's quite fast and quite nice in the right lighting. But if the light comes from a bad angle, then the contrast is not so good.
It has a very pleasant retro sort of feel to it.
Yeah, definitely. And of course, the crank is a nice gimmick. But I'm not using that in PUP because the PUP doesn't have a crank either. But yeah, that was just a quick update about that. I've done that a couple months ago. Oh yeah, thanks to Shipper. So I show you my other project that I'm working on right now. And because I think there's a bit of an overabundance of electronics projects on Makercast, I figured I'd come and bring a wooden project once again. And that's this. So as you can see, I've been obsessing about puzzle pieces again and made some strangely shaped ones here. So which one? This is a nice one to show. So their basic shape is square, and at the top they have 3 connections, and at the bottom they have 1 connection. And they are colored in black and white. And if, for example, at the bottom, if you have a blank at the bottom, then it's black, like these. And if I have a tab at the bottom, it's white, like this. And vice versa at the top. So I've already assembled a little patch of these here. So let's see how we can continue that. You need to observe that I have used periodic boundary conditions here. So the left edge and the right edge line up. So the left neighbor of this piece is this one. So here I have the 3 pieces that are white, white, white. So I need to find one that connects to white, white, white. That's this one. And so that goes here. Then here I have white, white, black. So this one fits here. And then I have white, black, black. That's this one. And black, black, black. That's this one. Black, black, white. Black, white, white. And here it would be white, white, white again. So it would be this piece again, but I've run out of these. I only made 8 of each piece, and as you can see, I already have holes up here because I didn't have enough of those. So let's leave that up. Yes, the shipper, that's correct. I'm going to explain that. And bitlinear, yes, they overlap. They consist of several layers. I explain about that as well. So yeah, when you put them together, they overlap. But let's continue here first. So this one is black at the bottom of my side. It's the same as this one. So I have black, black, white here. And then black, white, black. And white, black, white. And black, white, black. And I have 1 piece left that does not fit here, but it will fit over here because, as I said, this one will be black at the bottom. So as you can see, there's only 1 piece that fits in any particular place. So the whole arrangement is completely determined. If you choose the top row and you observe the periodic boundary condition, then the whole pattern is completely determined. As you can see, some kind of interesting pattern shows up here. And this, as the shipper already guessed, this is an elementary cellular automaton. I'm not sure if you're familiar with elementary cellular automata, but you have probably seen pictures of them. Let me show my screen. The shipper, can you show my screen? Thank you. So you have probably seen pictures like these, I guess. Such a cellular automaton works in the same way as I've shown with my puzzle pieces. the color of every pixel, whether it's light or dark, is determined by its 3 neighbors in the row above by a certain rule. And then once you choose the top row and choose a rule, then the whole thing is determined. There are 256 possible such rules, and most of them don't do anything interesting. I can show you this. This is all of them plotted out. Most of them just make some vertical or diagonal line or something, but there are a couple of them that make interesting things, such as this rule, that is rule 30. And as you can see, it makes kind of random looking chaotic stuff here, which I find fascinating, because the whole thing is totally determined. Once you choose the rule and you choose the top row, then everything is determined. There's no randomness. And still it makes these chaotic stuff here. And yeah, as the Shripa said, this is actually 1D cellular automaton, so you can regard this as the temporal evolution of a 1D row of pixels with time running from top to bottom, similar to how Conway's game of life is the evolution of a 2-dimensional grid of pixels with the new state of each pixel being determined by its neighbors in the previous generation. Yeah, right. There are actually seashells that grow in this way and make such patterns. I found that when I looked it up on Wikipedia. So for this picture, the top row was chosen as all white with 1 black pixel in the middle. That's what makes this triangular shape. You can also choose different starting conditions, like you can fill the row randomly. I can show you that. I'll make it random here. So this is rule 30 with a random starting point, and you can see it makes same kind of patterns. What was using for the puzzle here is not rule 30, but that is rule 105, and I can show you what that looks like. So this is rule 105 with random starting points, and I like this pattern because it makes quite a variety of patterns. It can make horizontal lines, it can make vertical lines. There aren't that many of them here. A couple here. It can make checkerboards. It can make dark stipples on light backgrounds. It can make light stipples on dark backgrounds. And so I found that interesting for making a physical realization of it. So back to the puzzle. Let me get rid of that. What you see here is not the final product yet. It is just a prototype that I made to figure out a couple of things. And one of the things I figured out is that it takes a lot of work to make all these pieces. And I only made 64 of them here, but to get a patch of a reasonable size, I will probably need a couple hundred. So I will need to find a better way of making these. These are laser cut plywood, and as you can see, it's 3 layers. So 64 pieces times 3 layers is already 192 pieces of plywood that I need to laser cut and then wash. Do any of you wash their laser cut pieces? I think I'm the only one who does that. I find that's just the easiest way of getting rid of the smell and of the sticky edges. Anyway, so you cut these and then you have to glue them together, and that's a lot of work. So maybe I will try CNC milling for the next piece, for the next prototype, or maybe 3D printing, although I like the wood just better than I like plastic. Another thing I figured out using a prototype is that I don't actually need these 3 layers. I chose three layers because one of them connects to the left neighbor, and the middle one connects to the top neighbor, and the third one connects to the right neighbor. But it turns out that's actually not needed, because the reason you need several layers at all is that this piece needs to connect to this piece, and this piece needs to connect to this piece. So these 2 connections cross. That's why you can't have them on the same layer. So you need at least 2 layers. But the straight connections, these don't cross with anything, so they don't need their own layer. They can be on any layer. So actually only 2 layers are needed. So my next prototype will only have 2 layers, and of course that will already help a bit with the amount of work. Another thing I found out is that precision is a problem. So to have these pieces go together smoothly, they need to be really precise, and that's hard to glue together these layers precisely enough. I made this jig for it, where I can place the 3 layers in it, and they're approximately lined up, but it's still hard to get it precise enough. Also, the laser cut is not really precise enough. The laser cutter I was using, we have at FabLab, is a self-built laser saw, and it has a little bit of backlash, maybe 1/10 of a millimeter or so. And I didn't optimize the order and direction of the cuts here, so they were kind of random. And so some of the pieces are 2/10 of a millimeter larger than others, and that makes them jam. So I'll have to improve that. And finally, another thing that I found, I can show you this if I can separate the top 2 rows here. That should work with the ruler here. Perfect. So the problem with this top row is that it doesn't hold together. It falls apart here in the middle. This piece holds together, and this part too, but along these edges it doesn't hold together. And that's a bit of a bummer, because this is a valid arrangement, and I really like the patches to hold together in all valid arrangements. But I can fix that by changing the shape of this S-curve here. If I make it curve down in the middle, so that there's a bit of a hook that holds the pieces together, then that should work better. Yeah, that's what I found out using this prototype. So next thing I'm going to do is redesign this and make a next prototype, and then maybe on one of the future Makercasts I'll have a couple hundred pieces of a working cellular automaton puzzle to show you. That's all I have.
So do you already know what the pattern is going to be? So did you calculate that beforehand? Will it be the same like the one you showed, or is this like you made this and you don't know the pattern yet?
The pattern depends only on the first row you choose. So if you choose that randomly, you'll get a different pattern every time. But if you choose in a certain way that you have pre-calculated, then it will be the same pattern every time. So it also depends on the width of the patch you choose. I mean, on my screen I had a very large patch, but if you have a very narrow patch, then there's only a small number of patterns that can occur, as I've discovered. In particular, for 7 tiles wide, as I have here, there's only basically 2 patterns that occur only in different translations. So this is one of them, and it's actually periodic. Let me connect this again here. If you look closely, you can see that down here it starts repeating, but in the inverse colors up here. So here's a row with only a black one in the middle, and here's a row with only a white one in the middle, and then it repeats the same way inverted, and then one pattern down below it starts repeating in this color scheme again. So most of these patterns are actually periodic. Well, all of them are, I guess, but they have different periods. And if you choose other widths, then sometimes there are more interesting patterns, and sometimes there aren't. I haven't really experimented to explored everything yet.
Well, I guess you could do another Python program to see.
Yeah, sure. I mean, that's what I was doing on the screen I showed. I wrote that in a Jupyter notebook, and that's what I used to play with. Yeah, right. The ship with the rule 30, the one I showed in the beginning, that one is Turing complete, so you can use it to do computations. But I guess the patches you need for that are pretty large, and probably wouldn't be able to realize that with puzzle pieces.
Awesome. So if we don't have any more questions from the chat, I would suggest for Kevin to show us his project he's working on.
Great. Everyone, I shall jump over to my pre-prepared slides. So I want to show you my virtual pet that I've been designing. I call it the Pico Tamachibi. It's based on loosely on the Tamagotchi craze of the 1990s, was it? So yeah, I was looking at designing this. I've always wanted to do like a custom PCB for this, and the very first version I did was just on some sort of Vero board. So what I wanted to do when the Raspberry Pi Pico 2 came out, which has got twice the amount of memory and twice the amount of sort of processing power, I thought this is perfect for this, because I ran out of memory whenever I was doing animations on the Pico, because it has like 264K of RAM. It's not very much at all. And these little animations, even though they're 1 bit, they can really take up quite a bit. So I'll show you the design of it. I'll show you the interface, which is the fun part, and I'll give you a bit of a demo of it as well. So if you want to play along, if you want to look at this project, you can head over to kezrobots.com/blog/picotamachibi2.html. So yeah, the design of this. So I used Fusion 360 to design the 3D printed case for the original one, but you can see there it's simply got one of the SSD 1306 screens. It had a piece of Vero board that I'd cut with a hacksaw, and it has 3 tack switch, momentary push buttons on there as well, and some janky wiring to the Pico. And the Pico was just loosely connected to the Vero board. And then there's no battery in this. It's simply just plug a USB cable into the top of the Pico, and you can start playing from there. So I did this one about 2 years ago, and when the Pico 2 came out, I thought this is a perfect time to revisit this one with a new design, with a custom PCB. So you can see that a simple design that I made in Fusion 360. I've got the original PCBs here. I'll show these in a bit more detail in a second. But yeah, electrically speaking, very, very simple. It's just 3 buttons, the Pico on the screen. There's no need for external power or anything on this one. And I think this is only about the 4th PCB I've designed, so they are still very simple as I'm learning the tool. I'm using Fusion 360 electronic design for these, just because you can design the board outline, the case that goes around that board, and all the parts and everything in one package. So nice and simple. And here's the schematic of that. So you can see we're not using very much GPIOs from the Pico. It's just the A, B, and X button, and then there's a clock and a data pin for the screen, and it just uses the 3-volt out on the Pico for powering the screen. Nice and simple there. So yes, so Bolly's made a really good point there, and I'll get to this in a second, because I made a bit of a mistake when I got these printed. So yeah, the Pico 2, the reason I picked this one, the original one was based on the Pico. The Pico 2 has got twice the amount of RAM, so this has like 520K of RAM, and it's got almost twice as fast processor. So all those little animations and saving and loading from the file system on the Pico much quicker, and therefore we can add extra animations, extra gameplay, and things like that to the project. So I thought that was a good way of introducing this. And the wiring, like I said, is very, very simple. It's just a single GPIO pin to each of the tack buttons. There's no other resistors or capacitors or anything like that. We can do all the debouncing in software for the button presses, so there's no problem there. Now, when I did this diagram, I did in Fritzing, and when I brought in the OLED component, I think it was a SparkFun component that I bought for the I brought in for the screen. So let's see if I've got one of the screens spare. So these screens, now I bought a whole batch of these screens. I've got about 10 or 20 of these screens, and I just assumed that the pinout was the same as what was on the diagram. So on the actual pinout diagram on in SparkFun, when you bring this into Fusion 360, they're in a particular order, and when you put them onto the, that footprint goes onto the PCB when you manufacture it. I thought that would be exactly the same as these ones that I bought. So if I just go back to me for a second. So this is the original PCB that I designed. You can see there's 4 pins sort of in the top middle, and you can see the Pico pins that sort of run top to bottom, and then to see the back there. So the Pico actually goes on the back, the screen goes on the front. I've not 100% thought that through when I was actually designing it, because the pins are kind of pointed in different directions, but it was okay as it turns out. but that was something I learned. Anyway, so I made the first version of this. I plugged it in. The Pico was working fine, but the screen didn't work, and the screen was getting very hot. And I thought, quick check with a multimeter, and indeed the voltage and the ground were swapped, which isn't great. So I had to do a bit of a redesign just to swap that over and basically design my own. And on the second version of the PCB, you can just about make out there's some text on the PCB, the silk screen, for the voltage, ground, clock and data, just so I could verify that, because it's quite difficult to check them sometimes when everything's sort of wired in. And yeah, Pico this side on the back of the board as well, just to sort of illustrate that to people if they're going to buy these. So that was the the mistake I made. I just assumed that there'd be a standard for these, which there wasn't. So the user interface is the fun bit. I had so much fun putting this software together for this. So just like the original Tamagotchis, there's like a little toolbar at the top. So I created a little icon class in MicroPython, a toolbar class that collects them together. You can adjust the spacing, you can adjust the inverse, so you can make them look like they're enabled or disabled. You can even have them flash. And then I designed lots of other little icons as well. So there's a little skull there when you get low energy, if you've not interacted with your pet for a while. And you can see this little poop in the right-hand corner. And I spent way too much time animating that as well, drawing that out pixel by pixel. And then the icon sizes. So I went with a 16 by 16 pixels, nice and easy to work with. I use GIMP to design these. And one of the reasons I use GIMP, not because I'm a hater of Photoshop or anything, but it can export to these .pbm files, and you can read them in MicroPython, and they're very easy to work with. So it just lent itself to a quick kind of design thing, save it out as a PBM, load it into MicroPython, and then displaying it on the screen. So really easy to work with. And they're very quick to load as well because they're quite small. So yeah, designed a whole bunch of nice graphics there for each of them. So these are the toolbar. We've got a food one for feeding your pet. The light bulb will make it go to sleep, or if it's asleep, you can wake it up. There's a game. I've not really done too much with the game yet. I think that's an area for expansion. There's a first aid one, which just gives it some more health. And the health and the happiness values will decrease over time. So if you don't interact with it, events will happen based on that. The toilet will just clean off that little poop that appears on the screen. The hat will give it some more happiness and health. And the little call thing just sort of animates. There's like 3 different states of that. The faces are off, the faces are both lit, and the faces intermediate flash. One flashes on, one flashes off. It's sort of intermediate, so it can kind of call you. So that's the sort of toolbar. And yeah, you can interact with it through 3 buttons. I think the original Tamagotchis had 3 buttons, and I thought, I'll go with that because we can have an A, B, and an X button. So A will progress you through the toolbar, B will select the item and activate it, and X just cancels whatever you currently selected. So if you pressed it all the way along, you can press X and it'll go back to the beginning again. So nice and simple interface. And then the files themselves, so there's an icons.py that contains all the classes in MicroPython for the icons, for the toolbar, for animating things, for receiving button presses, and for events as well. So events are things that we might want to happen and coordinate, orchestrate those things happening. The picotamachibi.py is the main program that runs everything, and then there's all these .pbm files for all the different sprites, all the different graphics. And there's an SSD 1306. I don't think that existed in MicroPython when I originally created this, so I'd sort of just hacked that together through I2C, and that seems to be working fine. So I'll show you in a second demo, but if anybody wanted to sort of follow along, I'm all over social media, so you can take a screenshot of that if you wanted to follow me on all the places. And if I now go over to the screen, let's go to the overhead. So I've got a couple of the prototypes here. This is the one that had the in fact, I think it's that one is the one that had the screen. So it's a shame because the Pico 2, they're about $5 those. It's not that easy to sort of get off, so that's where it's going to live forever. This is the actual prototype I had, so you can see there the screen, all the wiring back to the Pico, and then the 3 tack buttons there. And then these are the ones that are actually working. So I've got one here. So you can see there it's currently asleep, and there's a poop on the screen. So if I press this select button, you can see there the menu bar, and it's just simply, I think I've shorted it out. Let me just restart this. It does need to be in like a case really, because I think if you short it out, it just resets. So if I've currently got the food one selected. If I press the B button now, you'll see it gets like a little energy. I'll just show you that animation again. Oh, he's just in a poop as well. If I press the button, you can see like a little donut falls down from the screen, from the top of the screen. I'm not showing what the energy levels are. That's kind of a behind the scenes working thing. So I think what it is when I touch these little mountain things, I think they must be shorting to ground or something. So I need to check that out. Maybe let's try not to touch those. So if I go to let's say the poop one, that'll just clean off if there's anything on the screen. It just resets that state. And if I just cycle back round to the sleep one, so I'm trying to do this at the same time with one hand, and it's not that easy to do. Right, let's just try that one more time. There we go. And if I press that, it'll now go to sleep. So it says night night, and then we get the little sleep animation there as well. So you can see there on the back, we've got the Pico 2. It's got a bit of blue tack, so when I've got it on the desk there, it sort of stays put like so. And I made a second one as well, just before the stream, just in case the other one didn't work. So that's the project I've been working on. It was actually quite difficult to choose a project to show today, because I do a different project each week for the live stream. And I thought I'll just show you this one because it's quite a fun one. It's a bit of software, hardware, all the different Maker things covered off there. So did I see a question there? So Nick says, any plans to add simple sound at some point? Yeah, so I was looking at sounds. There's a few different options on the Pico. We could either have like an I2S sound module that we could add in, and you can play like WAV files and things like that. I know Pimroni have done quite a few things with sound using that, and Adafruit as well. Or we could go for a simple buzzer. I've got, I think, some active and passive buzzers in my sort of collection of bits and bobs up there. I've just not got around to adding those in yet. But yeah, sound is definitely something we could add to that, particularly with a Pico 2. That shouldn't be a problem. So the game, which game was the source for the game icon? What did I choose for that one? Let me just have a quick backup and see what we put on there. Is it baseball? Let's go back to that for a sec. Is it supposed to be like a ball and a bat? It's quite difficult to design things in 60 by 16 pixels. So yeah, that was the one. A couple of other projects I've got, you can probably just see behind me. There's a one just there that I took to open source in San Francisco with me. That's Voltara. And that's like a miniature version of the Zoltar fortune teller. And that one uses a little thermal printer. When you press the arcade button on the front, it'll do like a little bit of an animation. There's like a little doll in there that's 3D printed. It sort of moves and its head lights up and there's sound and everything. And then it prints out a fortune using Python. Some Python. There's a Raspberry Pi in there as well. So yeah, that was another one I considered doing, but it's a little bit worse away from its journeys, that one. Johnny says buzzers are annoying, so do that. Love that. Any other questions was there that I missed on there? Let's see. No, I think that's it, isn't it?
You mentioned possibly making an enclosure for it. Yes. And in one of your slides, it was showing an enclosure. Is that something that you're working on now?
Yeah, so that enclosure, I very quickly 3D designed it, and I didn't design it to sort of stay closed. So it's like a very loose fit. And I thought, I just need to put some screws or some kind of, click mechanism when you push it together. And that'll certainly stop it from shorting out when you press the buttons. And I need to get to the bottom of that one. It might be because it's being powered externally rather than through like a battery or something. And the battery is something I was going to look at as well. I was just trying to keep the size down as well. So it's kind of that kind of size, the original one. But yeah. Great. Back to you then,
Yep. Thanks for your project. I used the Tamagotchi in my childhood as well, so it really reminds me of that. So you did a pretty good job.
Thanks.
Awesome. So I actually got some flip dots today. So I saved a few displays from different buses. I actually got different types and different versions from different companies actually, but I only have one working here with me today. But technically I have flip dot displays, LED displays, as well as LCD displays that were used in buses. So it will be very interesting to reverse engineer some of those and get them working with some ESPs. So one thing that I've put up here, camera not working, one moment. There we go. So these are all the panels that I've got. So the one up top is actually one of the LED versions, which is a side unit from the bus, which you would see from the side. The one underneath is also a flip dot side one. And then the big one below is the front unit, which is quite large, like almost 2 meters in width. And it has a lot of pixels. And down in the left corner, you can see also one of the smaller units that you would see in the back of the bus or on the right side or next to the side unit on the left, which just shows the number. To acquire these flip dot displays, you probably go to a scrapyard if they have some, or you have some connections like I do. So that's where I got them. They have like 12 buses or so, so I can get like a whole ton of these. These are all that I could fit in my car. But yeah, the protocol for this one, the panel, I don't know what the company was. Yeah, Lavo. It's a German company, I think. And they use what's called the Monobus 5. They also have a Monobus 10. I don't know yet what the difference between those two are, but at least Aaron, ATC 1441, if you know him, and we have been working on reverse engineering the protocol for this one. And if you can see it underneath the A of Makercast, that is actually another one of the side units that shows the bus number. And I have soldered an ESP 8266 to its receiving pin, because the Monobus 5 uses a 24-volt single wire UART for sending and receiving its data. The baud rate is 19,200 baud. And they do some crazy stuff. They have a, so for the protocol, they have a start byte, then a command byte, which the upper 4 bits are the command and the lower 4 bits are the address of the panel in the bus. So you can have up to, 8 different of these panels, I guess. And then you have some data and then the stop byte. And since the start and stop byte are the same and those have a special meaning, they added, so they also have a checksum at the end. I forgot about that. But the problem with having a delimiter like that is that whenever the delimiter comes up in the other data, then you have to do something about it. So what they did is they replaced it with a different character. Then they append the same byte after that, but remove some of the bits, so it's a different value. And since the now first byte, I think it's F8 or something, since that has a special meaning, now they also have to do something if that specific byte comes up in the data. So that one also has the same 2-byte replacement. But the interesting, or the most interesting thing about this is that that they build the package without replacing those bytes. Then they calculate the checksum. After that, they go through and replace all those bytes that are delimiters, and then they send it out onto the bus. So it's very old and it's very complicated. But at least I've got we got some code working. I will post the link in the chat. We did we made a GitHub repository for it. So if anyone is interested, you can take a look at that. And yeah, so for this one, I have a demo running, so I can just change all the pixels to blank. And the protocol works. That's also very weird how they did it. So you can see the IDE connector, the ribbon cable on the bottom right, and that connects to the rightmost panel. And then from there, it daisy chains from panel to panel to panel. So one panel is only, I think, what is it, 28 by 28 pixels. And then actually the first one on the left, which is the last one in the chain, is a smaller one, which is only 20 or something. I don't remember right now, but okay, my camera is now following me, so let's forget about that. And the addressing is also very weird, because the first panel on the right is address 0 to something, then the one next to it is address in hex 20, and then the next one is 40, 60, 80, and so on. And then you go from right to left again. But that makes it also very hard. So if you want to update the display from left to right, you have to jump around with the addresses and such, so it looks like it is being updated from left to right. But if you would just update it starting from the lowest byte going up, or the lowest value, then it would update the rightmost panel from left to right, then the one next to it from left to right, then the one next to it left to right, and then to the end. And since the first panel is a little bit smaller, you have to you skip the first two or the first rows and then start somewhere in the middle. So it's it's very, very weird how did we learn about the project, the protocol? So the front unit, maybe I will show it in the other camera quickly. So the front unit has this huge PCB in it. And the front unit, I will refer to it as the head unit, because that's the controller for for all displays in the bus. And this unit right here, actually, let me remove the cables. So this one right here has an FPGA over there, which does most of the stuff. And then actually the control circuit so they have two different ways of controlling these panels. So they have this, which is the communication with each individual panel, and they have some drivers on the panels itself. And then they have these two connectors, which can directly drive the individual flip dots. So this one will do instructions for the drivers on the board, and this one will do driving the flip dots directly. And what's also funny is that they then have a connector like this one. It's a 4-pin connector, and this one is actually the EBIS bus. This is a special bus for buses, for communication, like all the devices in a bus that show like the stations and do announcements and everything. They use this EBIS communication, and it does some crazy stuff. But we're not going to talk about that. And then also the monobus connector, which is actually the same type. I will answer your question later, Bolly. But yeah, this is the main controller, which will send out the packets to all the other units. And it also has a little test button right here, which you can press, and it will cycle through some, like, all dots are flipped, all dots are not flipped. Then they do a checkerboard and such. And this one also has a card reader. And you program the device with just plugging in a memory card here, and then it copies everything onto the FPGA, I suggest, or I think there's some flash memory down here. It will probably copy it over, and then it knows what to display for each station. And yeah, what's also very funny is they use a 4-pin connector, because one pin is signal ground, then the other pin is the 24-volt single wire UART for the communication. Then they also have an 8-volt power supply for the other PCBs, which are in the other units. And then they also have a 22-volt, I think 250 milliampere supply, which actually flips the dots. So the part right here, this one supplies the current for actually flipping the dots. And this bus is connected in a star configuration. So this one just goes to a distribution panel, and from there, every other panel is plugged in. So it's a very crazy design. And how we learned about all of this is just, I just hooked this up and then used some cheap logic analyzer, the one for $5 from Amazon, to just sniff the signal. And then I gave it to ATC or Aaron. And we know that he loves to figure out how these things work. And then like one day after I sent him the dump, he pretty much had mostly the whole protocol and the web version that would decode the packets. Well, at least for some special versions, because there's also a different, there is a first, the protocol, you send a special command with some data that sets up the communication, and after that you can send the data column-wise to each of the panels. And depending on the first command, the data that follows is specified. So they encode in 2 bytes of data. They encode. Oh no, it's the camera is just doing some gesture stuff. Funny. So they encode 7 pixels in 1 byte, but the lower byte encodes 8 pixels and the upper byte encodes 7 pixels. But I've seen a different GitHub repository where they also reverse engineered the stuff here, and they sent a different packet before, and they put 2 bytes and 16 pixels of data in there. But for some reason, 2 bytes and what was I saying? No, they have 2 bits in each byte is 1 pixel data, and the 1 bit says flip the dot or not, or power it, and the other bit, I'm just so confused. The other bit says flip it or don't flip it. So you can actually send the data for flipping or not flipping dots, but actually not flipping them, because you have to either have both a 1 or a 1 and a 0 for black. The different protocols are depending on the initial sequence, and that's also one thing that we have not figured out what it's actually doing and setting up and such. So in all my examples here, or my stuff that I have here made, I will just treat it as a special command that has to be sent first, and then you can send out the data for the whole panel. And yeah, it's very difficult how they did everything. How can we make this as complicated as possible? Yeah, probably because they don't want you to hack it on the bus and show different, I don't know. So my next goal is to actually make a PCB that will emulate this whole thing, that will provide the 8 volts supply for the other PCBs, as well as provide the 22-volt signal for flipping the dots and the data. And then also design another board that is like the one in the other units that will directly control the pixels, because I think that will give more freedom, and you could also do your own protocol on that. And if I flip back to the camera, I also prepared some other demos, so I can just flip all pixels to yellow, and that's actually as fast as you can update the whole panel. So you have to wait. So you can send one column of data, and then you have to wait about 30 to 32 milliseconds before you can send the next column, and so on and so forth. Technically, the PCB or the client answers with an acknowledgement after you've sent data, and that means I flipped all the dots. You can send me the next data, but with the 30 millisecond or 32 millisecond delay, you can just omit waiting for it. So I'm just using the transmit pin and spew out data, and I don't really care about what's being sent back. But if you want to have this protocol as fast as possible and update the panels as fast as possible, you would have to wait for the acknowledgement before sending the next row. But yeah, these 28 by 28 pixel matrices make for perfect display. So, I mean, putting this up in your living room or something is a little bit big, but I actually made so this would look great in the man cave. I also don't have the original casing it comes with, because that weighs like 50 kilograms or something, because it's all metal and steel and welded together and screwed together, so it's very, very heavy. So in this case, it was easier to just pop off the panels from the back, screw out all the parts, and then just take out the individual panels, because it's easier to move around. But yeah, these smaller panels actually could be used for a small home assistant display or something. So here I just have a demo that will take the current weather data from some online service and actually display the current time. And then the weather data is updated every 5 minutes, and the time, well, every minute, so you can see. And for this one, I've actually designed my own font to go on there, because yeah, that the fonts that were online, they didn't really fit 3 lines on there. But as you can see, it's quite big. Yeah, you could display bus schedules on that. The only thing that is not great about this displays is that they take a long time to update, and that's probably also why we don't see them anymore. And you can't really do scrolling text because it really takes a lot of time to update. So playing Snake on it or any games would technically be possible, and you would need to, well, I would recommend building your own PCB for controlling the dots individually. Yeah, fonts are so much fun, and they take a lot of time to make. So also all the special symbols. But there is actually a website that I found that makes it very easy to work with these fonts. You can just type in the characters that you need for your font and then play around with it. I don't know if you, but I don't know the link right now. Yeah, but for something like Snake to work on there, you would have to have a custom PCB so you can control the dots individually and don't have to send each column every time. But for a small display like this, like 28 columns, it's quite fast to update. It doesn't take like 10 seconds or something for the whole thing. If it's possible, some only allow resetting rows at once or even whole display. Yeah, maybe the controller has some special command for that, but while sniffing these displays, we didn't really find any of that. What's also interesting is that the head unit doesn't really care about the connected display, because initially I thought there must be some kind of protocol, like who is there and what kind of display are you, and then the head unit decides on what to display on these. No, actually, the head unit is hard coded or programmed by the memory card. So it knows on address 1 there is going to be my head unit. So address 1, you don't see the data for address 1 on the bus. It just displays it directly. And then for every other address, it will send out the data. And to get more sniffing data, or yeah, to work with for reversing the protocol, I just tried playing around with the addresses on the device. So if I switch back to this camera, if you can see, there's underneath the D sub connector right in the center. Where is it? There. There's this selector, and with that you can actually select the address of the display. So what I did was I just changed the head unit address to 2, and then the client device to 1, and then it actually sent out the data for the whole large panel. So it doesn't really care about what is connected. It just cares about the address, and then whatever configuration is set up for that address, it will just spew out the data for that. But it will check if the device is there. So if the device doesn't answer with an acknowledgement, it will try a few times and then give up and move on to the next display. So it's crazy how ATC figured all or most of this out, and the few bits with like the special characters and such, that's actually what I figured out, because sometimes some of the rows were updating, sometimes they weren't, and that was the case when the limiter character was found in the data. So yeah, there's still a lot of work to do, because there's the other monobus 10 that we have to reverse engineer, and then up top you can see the LED matrix, which is from a different company, ASYS, or AESYS they are called. But actually I found a GitHub repository that also has some code for it, so I just hooked it up, but it didn't really work for my display. I guess it's a different version or something. It looks like it would be the same, and I don't think that the company really redesigned the panels and the communication of it, but it doesn't work for me. So yeah, that's the flip dot display. So were there more questions that I just skipped? Maybe some different pixel mode, just only change. It depends on the panel. Mine only resets colors. Interesting, yeah. Good. I guess, do you know, Bitlooney, what company your displays are of? Would also be interesting to see. Or did you get them from a bus actually, or where did you get them? That's something that would interest me now. And also I can explain, so the side unit you can see there, the one that shows 202A10L, those data, or that indicate, this is what is initially shown by the head unit when you first power it up. So 2 is the address of the device, but this data gets sent to it by the head unit. So this is actually, it's not like display your configuration. So all the devices are just doing whatever the head unit is saying. So there's no data storage on there. There's just a program on there that will interpret the commands and then display whatever the head unit says. And it doesn't really know what is actually connected to it. It will just send out the data over the IDE connection. And up there, the 2 means that it's device 2. And I think the other characters mean which configuration is loaded, because these devices can actually have multiple configurations loaded on them, which you can switch between. Only got this one smile from a bus with no driver. Ah, too bad. So what was the other one? Christ, and we get the decks out. let's put some tunes on. All right, so I will come to an end now because I could talk over this the whole weekend, I guess. And there will be no quiz today, but I actually prepared some questions for our guests, and we have to see how this goes. So you can answer the questions if you like, and if you don't like the question or you don't have an answer for it, it's no worries. So the one question, I got 3. Let's see how much time we got. Half an hour left technically, but so the first question for you guys is, what's the most memorable or unusual material you have ever used in a project?
There's a whole lot of silence here, I'm noticing. I'm sitting here thinking about possible materials. There are many different materials I've used, but I can't think of any that are unusual or specifically memorable. There are different materials that all have different properties. I suppose one that I have a very small amount of experience with and enjoyed is foam board. A couple of years ago, I helped a friend build a remote control plane out of foam board, and I just found it a really interesting material because it's light, it's cheap, it's fairly rigid, it's easy to work with nothing but a knife, and yeah, it was quite a fun thing for mechanical construction, but it's not something that I've done anything much with. I have very little experience with it. So in terms of interesting materials, that's probably one that I would classify as interesting to me, at least.
So I think for me it would be when I created this LED dog coat, my little Chihuahua. So it has like a little saddle that's got a Raspberry Pi Pico on it, and a little battery holder as well. I had to test that this didn't get too hot because I didn't want him getting cooked. But yeah, trying to get these LED strips to stick to this transparent plastic coat was not very easy. So I just tried super glue. But yeah, it does kind of come off a little bit. So I'll be working on that again at some point. This time of year, when it starts getting dark early, this is a great time. And what I intended to do with this one is have like scrolling text across there. So it's an unusual kind of pattern because the, I don't know if you can see there, they kind of zigzag up and down. So addressing pixels, I had to come up with like a formula for, you know, addressing that pixel or that pixel there. You have to figure out what direction it's kind of going in. So I have got kind of X and Y coordinates, so I should be able to sort of scroll text on there. And also this has a Pico W on board on the little saddle, so I should be able to connect to it from a mobile phone and control text and colors and things like that from there. So yeah, working with this was probably the weirdest, trickiest one.
Kevin, what code are you using for driving that?
MicroPython. So pretty much everything I do is MicroPython, just because it's very easy to work with and very quick to get running because you don't have to compile it. The only snag is it can be quite slow for certain applications. So you can't do like video with MicroPython. You couldn't use like an ESP32 camera. You can take a still picture, but you can't really do video. But for everything else, if it's just turning on pixels, great for that kind of stuff.
Yeah, BitLooney just pointed out that WLED does that in matrix mode. I think that's in reference to the zigzag pattern. I've seen LED driver libraries that take that into account. And you can do zigzag horizontal, zigzag vertical, left to right, etc.
Yeah. Yeah, like I said, I did come up with the formula for positioning pixels on there, so I can turn any pixel off at any X and Y coordinate. They're not quite... There are more pixels going down than there are across this big gap, so it doesn't lend itself to like a picture being on there, but yeah, it's very bright. I think there's a video clip of that on my YouTube channel somewhere. Anybody wanted to check that out? What was the other question there? Let's see it for the dog. So yeah, it's a Chihuahua, a little Chihuahua. I don't know if he's on my... He's currently in the house. I'll see if I can find a picture of the project. Let me just find it on the So in fact, if I share my screen, let me just bring this down here. So this is my website, kesrobots.com. If we go down to pets and the ideas page, ideas and then pets, we should be able to find the project quite quickly. There it is, Cyberdog. So there he is. There's a little saddle, and there he is wearing the coat. And you can see there, the LED strips was probably the expensive part of it, but everything else is pretty straightforward. The saddle was designed in Fusion 360, and there you go. There's the numbering system for it, and how everything sort of gets wired together. There you can see it in action. There we go. I'll sort of zoom in on that one.
What are you using to power it?
So for power, it's let me just go back to the full screen. So Pimroni do these really great batteries. So it's a little 400 milliamp hour battery, LiPo battery, and that's like a little LiPo charger, and that just provides power directly to the Pico. And there's also this Plasma 2040, which is a product Pimroni do, which just makes it really easy to plug into LED strips. I could probably merge those two together now. In fact, I think Pimroni just brought out a new Plasma 2350, which is the new chip from Raspberry Pi. So yeah, so that battery works for about half an hour. It's surprisingly powerful.
I mean, we can also expand the question to components, if materials is like a weird. So are there any? Oh yeah, Christian.
I don't recall working with any particularly interesting material, but I've had an idea once to make a display out of sand. Maybe that would be an unusual material to have a mechanical thing that drops sand in certain places and not in others, and use that to display things. I've already bought the sand, but I haven't done anything with it.
Almost done.
Right.
Right. So the next question, I guess, will be then: if money and space were no object, what's one piece of equipment you would add to your workshop?
What's the name of those robotic hands you can get? I know Raspberry Pi use them in their factories for sort of pick and placing things. It's literally like two hands. I'd have some of those.
You don't mean a pick and place machine, or?
Not pick and place. No, it's literally like two robotic hands with very dexterous connectors on the end, and they can work together to assemble very complicated items. Yeah, I can't remember what they're called, but yeah, something hands, I suspect. I'd have them.
Well, I have a bit of a fanciful answer. You said if money and space was no object, I would like either an electron microscope, just because I think it would be fascinating to look at things in the very, very micro scale, or maybe a CAT scanner, like a CT scanner.
For the PCBs?
Not necessarily. I would just like to put things in it and look inside them. I want to see cross sections of objects. So I already have pick and place machines and all of that sort of gear. And the practical answer would be, oh, a better reflow oven or something like that. But no, if we're going totally fanciful, just money doesn't matter, space doesn't matter, I think something like an electron microscope or a CT scanner would be fascinating. It'd be really fun to play with and investigate different objects and materials and see how things are put together. Or maybe an X-ray machine. That would be fun as well. A bit loony says space elevator.
I can't think of anything because that's a question that I never ask myself, because I do not have space.
Well, that's the the question. For me, it will probably be a pick and place machine, I guess, because well, I built one myself, the Opulo, or Lumen PNP now called, but it's just sitting in one corner and needs some love and attention, and I don't have time for that. So, like a real, yeah, reflow oven. What's it called? Like the setup you got, Jonathan, are probably like with the pick and place machine, the oven, and solder bath and everything, so you can just press a button and yeah, that that's probably for me, because I also don't have a lot of space. All right, so the last question, if you could visit any era in history or to gather inspiration or materials for a project, when would it be and what would you make?
You're really making us think.
Yes.
Okay. I would like to see, if I wanted to see materials and techniques, the era I would be interested in is probably late 1800s through to like 1940. That was an era when there was not really mass production. There was lots of hand fabrication, and yet there were incredible devices made. A lot of scientific instruments, clocks, and different devices that came out of that era. If you look at them now, and you imagine sitting down trying to make them yourself with original tools, they're just mind-boggling. It's the sort of thing that I would think, oh, I need a CNC machine to make that, and yet someone made it by hand to a precision that I can't imagine. And a lot of the tools in that era are made out of, were made with very finely finished timber, all beautifully cut, joins that you can barely see. So in terms of materials and techniques for inspiration, I think I would travel to the very beginning of the 20th century and see a lot of that craftsmanship and see how things were made that back then.
I think for me, what I would do is I would pack up a 3D printer, a laser cutter, all the kind of making tools, and take it back to Nikola Tesla and say, have at it. You've got all this equipment, make stuff, and see what he comes up with. Love to meet the guy.
I can't answer this question because this is the kind of question I can't answer on the spot. I need my peace and quiet to think about such things.
Well, I would probably go in a different direction and see what kind of technologies are there in the future and what changes from now. So will we achieve some major advancements in transistor stuff, or will there be something completely different we can't comprehend right now, like for example Star Trek or all the other fictions or science fiction actually. So what about, I mean, this happened before, so we have a few things that they imagined in the films and movies a few years ago that we have now. So what of other kinds of technologies that were shown there or now in movies that we will have in the future? So that would be probably interesting for me. Well, yeah. So those were all my questions. So I guess if anyone has something they want to tell or anything, yeah, just go ahead now, I guess. We got a little bit of time left, so but we can also end the stream if you like. So I'm leaving it up to you guys.
There were some questions from the audience.
Is making a hobby or full-time vocation?
Right. For me, it's definitely a hobby. And I mean, I work 80% in my day job, and I work about 20% running the Fab Lab. So there's about 0% left for actually using the Fab Lab.
Well, for me, making is also a hobby. I have my full-time job as a software developer, and the free time I've got, I will work on my projects and mostly take on new projects. And because actually at the moment I'm also working on like 5 or 6 different projects at the same time, which also do like PCB design, software development, hardware design, everything, and enclosure. So here I've got one thing that I'm working on. It's called a Skizzy Light, which is a USB like Skype for Business light that will show your current state. So it's red if you are calling someone, or if you are busy working. It's green when you are free, and other colors. But it's also well, I'm intending to make it open source, so you can just do whatever you like with it. It has an ESP32, I think S2, yes. So you can do some wireless stuff with it, and it has a USB-C connector. You can upload the firmware with the UF2. So it's very open source, I guess. Like you can do anything with it. But for the Skype for Business stuff, I actually made a Python script that runs on the host, and it will search for it, because I have some USB IDs I got from Espressif. I know you, Jonathan, you probably used them as well before, maybe. And then you can actually identify this device from the host PC and send commands to it and communicate with it, and put it automatically into the UF2 mode and do software updates from the Python stuff. And it will communicate with Skype on the host, and then get the information and display the color. Something
You
like
mentioned that software development is your full-time job, and you made the distinction between that and making. And I found that interesting, because I think for all of us, our day-to-day job, or what we are paid to do, to some extent, has skills and techniques that are the same as what we do in our own free time. And so it's a little bit of an artificial distinction, I think, that when we're at work, we're not making, and when we're at home doing those same things, then we are making. And I find that for me personally, my day job, doing contract engineering sort of work, it largely is making. So most of the time I'm being paid to do what I would be doing anyway, and what I love to do. And I think that's fantastic. So do you think that it's really a different mindset between when you're at work, you are being paid to work on a specific project for a client, you have specifications and requirements that you need to create a certain outcome, versus when you are working on your own projects and you can be totally self-directed and you can just follow wherever your imagination takes you? Do you see making as more of a mindset thing rather than a technique? I'm curious to know what people think about this.
Well, for me, the difference is like it's a different level, or like I do this professionally. I also incorporate what I know in making things. It's technically the same thing. If I sit here and program for my company, or if I sit here and program for my projects. But the one difference is, I think, I don't have to finish my own projects. I can do whatever I want. I don't have to implement a feature and it has to be done next week or something. Well, at my workplace, we don't have that kind of pressure, like you have to get it done tomorrow, or the customer is, because the software that I'm developing at our company is actually used by ourselves. So there's not this kind of pressure or anything, but yeah, I guess the difference for me is that the one thing is professional and the other thing is just making. And if something goes wrong, then whatever, you learn something out of it and you just go on. or if you can't do it, like on the work level, there is no you can't do it really, because you either get it done or you ask someone else to get help and get it done. I mean, it's the same with making, sort of, but sometimes you hit a brick wall and then you have to find some information online or something. I think it's a little bit
the consequences
different.
are different.
Yeah.
The consequences of failing at your job are a bad outcome, whereas with making, it's all about the journey, not the destination, and learning things along the way. So I think that's what I really love about it. It's the idea of I can go down this little rabbit hole and learn about something totally new. And there is no particular pressure to have a deliverable within a certain time frame.
Also, it doesn't have to work or just a little bit or just how much or like with the flip dots. Like you could go the extra mile and figure out what every command there is and what it does and what every bit exactly means or not, or you can just leave it like that because it works and I can display data, but so I don't have to go this extra mile. But maybe in a job you would have to figure out everything, like every little detail.
I think the opposite is true as well, in that in a job you might have a time and deadline. So I'm a project manager, freelance project manager for my day job. So it's quite cerebral, not very hands-on from a electronics and coding perspective. But I always find like ways of bringing that in. So if people need some kind of graphic creating, I've got all the tools for doing that here. If there might be something that I'll see and I'll get inspired by at work and bring it into the creative space here. But yeah, you can spend a lot more time than you would get that is kind of economic, really, in a hobby. So it doesn't have to pay for itself. It's nice if it does. It's nice if the things, pay for themselves in that way, but they don't have to. I think with a job, that's the point, isn't it? Keep you gainfully employed. But yeah, I always say like when you're making something, you first make it work. So, you hack something together and it kind of works in a really janky way. Then you need to make it right. So you might write it up, you might refactor your code, make it more understandable. So when you come back to it or other people use it, it's understandable. And then the third phase is like, make it fast, optimize it in some way. So you can, maybe if you're making a board, you make it so that you can make many of them and they all share the same components to bring the cost down so that you're really getting that efficiency. I think with a hobby, you can just live in that first make it work phase and never really have to bother with the rest. Although it's good if you write your projects up.
You forgot documentation.
Exactly. Exactly.
And most of the time, it's the make it work phase that's the fun part.
Yes.
That's the bit we all enjoy. It's getting to the point where it's like, oh, it's working. And then after that, it's all downhill.
Yeah. That's why it's good to return back to a project that you've been working on and maybe you've left for a while, because you can come back to with like fresh eyes, and it's surprising how much you do learn in like a year, and you can come back to a project and think, why did I do it that way? This would have been so much easier to do this. Or it might be a new board or new technologies come about to make that easier to do. I think you also go through different phases and stages. Like I've only just started creating PCBs. I know a lot of you already have done that for years, but it might be like a new material or a new machine that you have that you're working with, and that can change how you work and what you produce and how quickly you can produce those things as well. So, John's testing will be a lot easier now. He's got the Testomatic, I suspect.
And I think also it's iterative. So once you can theorize as much as you like, but until you actually start building something, you're just making educated guesses. So that's one of the things that I found over and over again. And that's why you see, for example, those two versions of the Testomatic is I had a picture in my head of what I thought it should be, and I built it. That was version 1. And I discovered so many of my assumptions were wrong and radically revised, and had to come up with a different structure for version 2. So I think part of the fun of that first phase you talked about of make it work is just build something. You need something as a starting point, knowing that you're going to learn from it. There will be things that you think will be great and they turn out to be terrible, and there will be things that just pop out of it unexpectedly that turn out to be the real high point of the project. Unexpected things. So diving in and getting started is the most critical thing.
Yeah, very much. And embracing that iteration. I remember when I started making, I wanted to make the perfect thing in the first go. So things like 3D printing, where it's like a real time sink and you've got something wrong, you've not put a hole in, or it's just that little bit off, or you've got to do the thing again. I used to hate that and not look forward to printing things because of that. But now I sort of embrace it. I think, what am I going to learn in this first iteration that is really obvious to me after I've finished it? So yeah, you just got to embrace the iteration, I think.
I think Christian also wanted to say something.
Well, coming back to your original question, the distinction I make is that the coding I do at work, I would not call this making, because it does not involve making physical things. I mean, I work in a company that does make electronics, but it's not me who made them. So the software I write just runs on a PC, and I don't consider that making. So that's the distinction I would make.
It's also the case for the big software project I'm working on. But we also got a different project that I started where I am developing a PCB, the software for it, the PC software to communicate with it, and it has motor drivers and it's solar powered, and it probably uses some supercapacitors for energy storage, and it's like a very huge project for one person to work on. But for my company, it's like, yeah, you can have some time, work on it, and if it doesn't work, it doesn't work. But if it works, it's great. We can have some bachelor things or that work on them, and yeah, that's like a side project at work. And that's what I would say. It's like tinkering, making something, but the software thing is just like programming. So any more questions from the chat, like the last one? I'm retired now, learning the things, new things with freedom, Nick said.
Yes, Nick, now that you've retired, you're probably going to be far more busy than when you worked full time.
That's actually what my father said. Now where he's retired, he has to do all this work all the time. And before he was retired, he had like some free time.
Okay, I will be the classic YouTuber person. Everybody like this stream and subscribe to Makercast.
Smash the like button.
Yeah, smash that. Yeah, that's right. I'm terrible about doing that. I never actually promote it. So yeah, smash that like button.
Well, I hope everyone enjoyed the stream. And as John said, smash the like button, subscribe to the channel, and share it on other media platforms and such. And maybe if you are a maker, because I've actually tried to reach out to more makers in the community, maybe come and contact us in the comments or anywhere else, and maybe you will be on the next Makercast. We would love to have some more faces here, and I think it really lives from more people showing off their awesome stuff, and will also inspire more people doing like tinkering and getting their hands on it. So thanks everyone thanks everyone for watching, and thanks to our nice and awesome guests for being on here and sharing their projects. And
thanks, Moritz, for hosting.
Yeah, even though we had some technical difficulties. And also, before I forget it, I will want to thank our producer, maybe you want to come on, Deshipu. Actually, that was the technical difficulty, that I wasn't able to host the StreamYard stream. So Deshipu was our producer in the background and switched all the scenes and camera angles for us. So also thanks a lot for your hard work in the background. And yeah, have a good night, everyone, or good morning in your case, John. And we will see you in the next Makercast. Bye.
Thanks.
Thanks,
Bye.
everyone.
Good night. See you.